Toplanan ve geri dönüştürülen boş plastik şişe, kullanışlı, şık bir çantaya dönüştürülebiliyor. Böylece plastik atık yeni ve değerli bir ürün olabiliyor. PAGEV, plastik sektörünün birleştirici gücü. Toplanan ve geri dönüştürülen boş plastik şişe, sportif bir tişörte dönüşebiliyor. Böylece geri dönüştürülen plastik atık yeni ve değerli bir ürün olabiliyor. PAGEV, plastik sektörünün birleştirici gücü.
Giving me the opportunity to present some of the research that I have performed. My name is Murat Büyük. I'm also from Sabancı University. I'm a researcher at IMC, Sabancı University Integrated Manufacturing Technologies Research Center. As Murat Hoca had mentioned earlier, can you hear me now? As Rakoja has mentioned earlier, this research center is an integrated manufacturing center. Although we are performing fundamental research, including finite element analysis, numerical analysis, computational mechanics, experimental mechanics, which are the foundation of composite research. When I mention about composite design, I also mean it's also somehow related to the plastics as well. I think they are all combined, especially in today's world, when we are focusing on thermoplastics. Okay, my research and presentation will be on composite design with a special interest on crashworthiness, because I believe design starts with crash and ends with crash, because crash is a phenomenon that provides the ultimate or maximum loading conditions for any structure, and these are protected by or dictated by regulations that your design should comply with crashworthiness because of safety issues. Therefore, there is just no interest for a design which cannot comply or satisfy the crash conditions or safety conditions. Therefore, any design starts with crash and ends with crash. Therefore, again, this is probably the maximum loading conditions that you will ever see. My presentation is in 3 parts. It's a little bit long, around 160 slides, so I will go very fast. Don't worry, this presentation is full of movies, so we will be able to see a lot of different applications, including, as you can see here, about the crashworthiness of a new car. This test and simulation has been performed with a joint research with National Crash Analysis Center in US, and this program is supported also by the US government, Department of Transportation, where we are actually performing new car assessment program testing, which you must be familiar with it if you have a car. If you ever bought a car, you should be aware of their safety ratings out of 5 stars, right? Any car, all the cars are actually evaluated according to this protocol and testing, and their performance is graded against 5-star rating. This is called New Car Assessment Program. So as you can see, in this program we are crashing cars with a given velocity and see their performances and their evaluation is also being performed, including the dummies inside. You can see that this kind of validation, which we call validation, is something that you validate your numerical model on the right against a real test result, which is on the left. So this is the ultimate goal for any computational mechanics approach, where when you have a validation, now you don't need to perform these very expensive tests again and conduct your research about safety and materials and maybe design later on with a validated model. Since you have validated here, now at the end this presentation will lead to, in the second or third phase, about how to actually transform this structure into a composite one. Here you can see also there are very different forms of vehicles have been also performed under this protocol, and their evaluation is graded again according to the NCAP ratings. You can see these are really very good validations, and you can see these numerical models are very well validated and quite efficient in obtaining the results about safety issues. And you can also appreciate that these cars or vehicles are built with many components, including composites and plastics. And you can see that the level of validation is quite good, that we can actually achieve a very good correlation with the test results. And this level of validation and is only performed by following certain methodologies where each and every component of the car is explicitly modeled. Here you can see graduate students, their job is to inverse engineer the components of the vehicle and test the materials, characterize the materials, and then build this numerical model for validation. This is not an easy task. This is not trivial. You can see this vehicle model is a numerical model, obviously, is made up of finite elements, which Eralp Hoca have mentioned. But the number of finite elements here are around 10 million. So the level of the model is around 60 million degrees of freedom. This is a very fine model. Every and each component is individually and explicitly modeled, including foams, metals, composites, plastics, glass, anything you can think of in a vehicle is explicitly modeled here. Even every and each bolt and nuts and spot welds are modeled, all of them, because you cannot achieve a level of satisfaction and validation without that kind of fineness and detail. Otherwise, this is not possible. You should characterize the material, the behavior of the material, all of them, and then you can expect some level of correlation or validation. Here in this institute, we have actually modeled a lot of vehicles and validated all of them. And these are also available in public research domains for international research purposes. Vehicles are not the only thing we have to think of about when we think about the crashworthiness or safety research. We have to include dummies, where we actually measure the metrics for injury. These are anthropomorphical test devices that are calibrated according to the human endurance limits, and therefore we can measure how much acceleration or force is being transferred into the occupants, which we can justify our injury levels accordingly. There is a family of those, obviously, so you have to characterize a lot of things. Safety research is expensive. Crashworthiness is expensive research, as I mentioned. Any design should begin with crash and ends with crash. Therefore, here you can see a lot of composite and plastic parts. Even elastomers are in concern. So that's the level of accuracy comes from the level of characterization. You have to characterize all the materials included here. In safety research, restraint systems are also in concern, and composites are again into the play. Airbags are composite, seat belts are composite, retractors are composite. We have to include those material information and characterization in place. Foams are composite. When we have a child seat, we have the foam, which is the only thing for a child to survive. Sometimes these materials are not enough because a dummy is made up of aluminum and rubber, but our material is human tissue, human is composite. Then we have to characterize human tissue. We have to perform cadaver tests. We have to model a human. Therefore, the active research in this area is now aging, for example. What happens to the human tissue and endurance limits for injury when we age? We have to test. And this is something very difficult. This research, when we think about safety, crashworthiness, and composite world, also involves the characterization and testing of concrete or geomaterials. This is probably the oldest composite as we know it. Concrete or research related to those kind of materials are also in our area of research. Here you can see protection barriers for protecting critical or strategic buildings behind, and the level of accuracy again depends on how much calibration or characterization you have performed on this material, and in this case this is reinforced concrete. Composite research is also very important when we think about high deformation rates. Here you can see a study on ballistics, and we can see that this speed of deformation based on the impact of the projectile is quite high. And we can see that there are different forms of failure, and that is not constant, that's not certain, it's changing, it's evolving, it's transforming. Therefore, you have to characterize the behavior of the composite material based on the fact that the high deformation rates really affect high strain rates, quite challenging. Here you can see a composite armor, which is an alumina-based metal matrix composite is used in front of the armor, and there is also a reinforced plastic behind it with a elastomer binding. Therefore, this is a very interesting composite research area that we have to consider when we think about design in composites and application in composites world based on the interest with crashworthiness or impact. Another area is civil aviation. In civil aviation, you can see some catastrophic failures have been seen in history, and there are countermeasures have taken according to these events. The civil aviation authorities have now dictated that every and each new engine should pass this very test, which you can see that the blades of the engine is released with an explosive at full RPM loading in very high speeds. And then you have to contain this blade inside the engine so that it should be no threat for the rest of the airframe. You can see this test is quite expensive. At least you are ruining one jet engine. And you can see the test chamber, right? So it's multi-billion-dollar test. Therefore, we have actually developed these numerical methods and numerical techniques so that authorities can accept to a level that the numerical results can be accepted as testing, and this is called certification by analysis, because testing each and every engine is a very difficult and expensive area of research. So we developed, as you can see, an engine model and have validated this according to the test results. You can easily understand that an engine have several different parts which are composites. Obviously there are other elements or materials, but it's a combination. It's a very sophisticated structure, but since you are characterizing every and each material according to this methodology and protocols, you are achieving a good validation, as we have seen. Birds are a threat. For those of you who are coming from Istanbul, should have seen yesterday, it was chaotic. I was very afraid. A bird is a composite structure, right? So how to come up with an equivalent bird structure so that we can assume its threat and design our structures according to this threat, vice versa. So threat estimation and modeling also somehow related to the composite design. Here you can see a bird impact being validated and tested and numerically validated for the Hürkuş. This is our very first airplane which has civil aviation certification. And you can see that wing structure is good enough to resist the loads coming from a bird threat. We talked about the high deformation rates for composites and plastics. This is a very well-known phenomenon that materials behave differently under different deformation rates or strain rates. Not only metals or polycrystals, this is also the case for composites and plastics. And here you can see this area is somewhat the area of interest for us. And for testing materials at those speeds, you cannot use conventional servo-hydraulic or servo-pneumatic equipment. You have to build equipment like this, which we call split Hopkinson bar apparatus. And these are for testing materials at high speeds. So when Eralp Hoca has mentioned that SU IMC have these capabilities, we are also under the phase of constructing these facilities in Sabancı University so that we can test materials at very high speeds. As you can see here, this is a 70,000 frame per second movie for a material in compression, and you can really see the shock wave propagating through the material, and material totally behaves differently. And this is the Hopkinson bar apparatus. Characterization that we have mentioned all the way from the beginning of this presentation is the key to the validation, and is the most important thing in composite and plastic research. I really have to mention that I'm coming from a computational mechanics background, but this mechanical testing laboratory, I'm the coordinator of this laboratory, and we are working with Eralp Hoca also under this research. So we know the importance of testing and experimental mechanics. You can't validate any numerical model otherwise. So we have a well-justified methodology and standards that we are following, and we have an accredited laboratory over there that we can test any material according to the required standards. And you can see the level of accuracy and validation for specimen testing here. Okay, again, when we come and talk about the aviation, we now know that this composites are very widely used in this area, and therefore we have to develop methodologies. And you can here see that the strain rate dependency of composite materials, independent of whether they are like glass reinforced or carbon reinforced, is strain rate dependent. Here the strain rates increase, I think that works, right? Okay, strain rates are increasing in this direction from the purple to the blue line, and you can see that that is somehow changing the behavior of the material. And the other interesting thing is composites are also state of stress dependent. Eralp Hoca have actually mentioned the formulations of those materials in tensor form, and we talked about the invariant space in terms of the composites, and you can really see that composites are state of stress dependent, and there is no well-developed methodology in the literature yet to characterize and model the behavior of composites under different states of stress. Okay, here also another material. One was glass reinforced, and the other was carbon reinforced. Both are strain rate dependent materials. Therefore, we have to measure those effects. Right now, there is no laboratory in Turkey to do that. Okay, we talked about the uncontained engine failure, or we have seen the test. What if we cannot contain this blade inside the engine? Then it's a threat for the fuselage, and you have to protect the fuselage. And we have used here, you can see fabric composites. We have used aramid or xylon or other combinations of different fabric composites. And you can see that the validation between the test results and the numerical studies. And another also approach to contain this blade threat is wrapping the engine structure with several layers of xylon or aramid fiber. You can see that this blade is arrested inside the engine successfully, but simulation was the tool here to determine how many layers were necessary. So it is so good in predicting the impact and crashworthiness of this airframe or structure. You can see here different numbers of layers have been tested in simulation form or platform for their performance. We mentioned about multi-scale approaches for modeling composites. This is also a good example to do that, all the way from individual fibrils and yarns. We call it in terms of micro level, and then a combination of those we call as meso, and the combination of different fills and yarns, we call them the whole structure as the macro scale. So our studies were good also enough to simulate those structures in terms of multi-scale modeling in length. You can see the anisotropy, high level of anisotropy is successfully predicted here. And this research is finalized with fuselage testing, protected with different forms or combinations of woven fabric composites. The second part of my presentation is actually I added last night when I was waiting for my delayed flight in airport, because when I came back from US and talked with the people from the industry, I have noticed that there is a need for deciding which parts can be transformed into composites or plastics from metal forms. They don't know, and they don't have any developed strategy or methodology to decide. Even OEMs or tier 1, tier 2 companies, they have no idea how to decide on which components should be actually in composite or plastic, so that we can construct a lightweight vehicle because of the concerns of emissions and reduction of the emissions, which is a regulation and motivation behind this. So I wanted to include that part in my presentation. This research also has been performed with National Crash Analysis Center, National Highway Transportation Safety Administration, which is a US government agency for Department of Transportation, and industry also backs up. This research is also now continuous with 2 national labs, Oak Ridge and Los Alamos. So in this presentation, I have to mention that we have actually worked on a Honda Accord vehicle, and our aim is 10% of the current retail price, and we wanted to see that how many parts and which parts should be manufactured as composite or plastic Obviously, this part is this vehicle is a mass production vehicle. It's almost like 200,000 annually produced, which is in millions in 5 years. So it makes a difference in the industry. So which one vehicle is manufactured every minute. Therefore, a decision on a transformation from metal to composite is quite important here. So you can see that when you are making a transformation from a metal, existing metal part, a lighter composite version, you have to pre-assume that it's gonna have some costs, but how much? This is the decision-making criteria for us. How much cost premium can you actually pay for it? And that also should have a reflection on the amounts of emissions that you are saving. Therefore, we have found that 10% of the costs is leading to an amount like this, and then it's either you save 150 kilograms and that will lead to a $10 per kilogram mass savings premium, or if you can save 300, then it's like $5. So that's what we will see at the end. But we have to first develop the methodology behind it. Here we have to start again from the coupon level. You can see this is a building block approach. We call it in aviation, it's very well known. You have to start from the coupon level all the way to the platform or vehicle. And you have to validate your results every and each step. Because you cannot compromise, especially from safety or crashworthiness, when you make a transformation from a metal to a plastic or composite version. You have to still make sure that the performance of the vehicle is not affected or changed or not compromised, at least in terms of safety. And how to do that? As you can recall, in the beginning of the presentation, we showed validated vehicle models, right? So the methodology depends on the fact that you characterize the material that you want to change. If it is composite, you test it, you validate it in the component and subsystem level, and you test it also in the vehicle level. But how? By using the simulations or the computational mechanics approach, because you have these validated models already in place, right? Here you can see every and each composite part starts from the design, and we also make into consideration the material information. We characterize it. The process parameters are involved, because when you're talking about plastics or composites, this is the key. Process matters. You have to also encounter or involve the information coming from the process, and you at the end perform the vehicle level testing in simulation platforms. Here you can see the material costs for the materials of concern, and you can see that it's like the material cost with manufacturing, process and scrap and manufacturing difficulties, all are involved in this measures or methodology. So you are not only comparing kilograms. This is the, I think, most difficult thing I have seen in the industry when I came back. They're comparing only kilogram to kilogram, so then the cost. But it's not only the material weight that's involved in transformation of a material or component. The process matters, the scrap or recycling matters, everything is matters. Even the manufacturing difficulties should be involved, the tooling, the joining technology should be involved. If you have a metal part, you might have an easier form of joining. You can use spot welds or nuts and bolts, but if you transform it into a composite version, your connections with other parts might have easily changed and get much more difficult and much more expensive. You have to also consider those changes. So it's not only the material cost or weight that should be concerned with during a transformation like this. And you have to consider the cost of the material in time, because it's a function of time, especially in today's world. You can easily understand, I think, what I say. The material prices have increased like almost twice within a month. So what is the gradient of the cost of the material? You have to plan accordingly when you are deciding. Clearly, for each and every material also you have to consider the maturity of the manufacturing technology. If it is like steel, you can see almost all the methodologies are mature enough to perform your production or operation, but when it comes to like plastics or composites, there is still some room. Sometimes it's in the long-term run, so there is still a gap, a delta for you to consider these materials for some of the parts for transformation, which means that still in today's world you cannot think about or consider 100% composite vehicle. Because these technologies are not still mature enough to do that. Then it's maybe a good goal or a futuristic expectation. Maybe it's gonna be coming, but we should be ready. But we should also be realistic that some of the parts will not change at all. But which one? We have to then invent this methodology and use for decision making. Okay, so this is now comparing the mass of the baseline vehicle, and for each and every subsection, here you can see non-structural weights. Here you can see the chassis, and now the powertrain and body structure. And here is the methodology. Methodology is quite actually simple, but still should be good enough for decision making. It's basically test all the materials, get information for manufacturability, design for manufacturability, design for disassembly or recycling, for scrapping, design or for connection parts that are going to be changed if any transformation is possible, and perform each and every analysis after a topology optimization, which you then create the load distribution or flow of the load within the main frame of the vehicle and design accordingly. Then you have the options to decide on the materials based on your cost premiums. At the end, that's gonna be our ultimate goal. Okay, here we then again invent 4 different options for a possible transformation and design. The first is the baseline. The vehicle is as is. Therefore, it's all advanced high-strength steel transformation. These are also very good materials, double face, trip, or complex face steels with high modulus are also a good option. The second option is you dissect the components of the vehicle into different materials. For example, the body can be high-strength steel, roof panel can be aluminum, floor panel or shelves can be plastics, or the rest can be also the plastics. The third option is aluminum intensive. The fourth option is full composite option. What if we choose that 4 different options? You can see that the cost increases are calculated according to those changes. So you can make a full composite vehicle, but the question is, are you ready for this cost premium or the increase of the cost? Or the market is ready or not? Whether it's not a question of whether you can do it, it's a question of whether the market is ready for the payment for this cost premium. So when you investigate in detail, you can see there are different options for the different components again, and at the end we have a lightweight vehicle, lighter weight vehicle, and these are the kilograms that you have stolen from the baseline or the existing vehicle. So like you have like 7.5 kilograms saving from the hood by just turning it into aluminum, for example. And this is the map of the whole vehicle. In terms of color coding, you can see which materials are used for which parts. So this study actually considers the whole vehicle. The study considers the transformation for each and every component. Here you can see the distribution again and the materials of interest. I'm just passing by quickly over here. I'm trying to come to the results. Okay, which is, okay, this is like topology. Also, you also work on the topology. And these are the tests that you have to make sure there is no compromise. Remember the fact that any change is subjected to the constraint that there is no compromise from safety. And these are the safety tests or new car assessment program tests, basically crash tests that you have to pass. Here you can see the vehicle and the stiffness of the vehicle after the cost reduction, the weight reduction. So the stiffness also is not affected or compromised. And you can see the natural modes of the vehicle. And you can see that the testing, the crash testing of the vehicle is also not compromised. You can see before and after. This is the signal for the actual test, the black continuous lines, and the dashed blue lines are the lightweight version of the crash pulse. So these are crash pulse. These are the accelerations that you are recording from your vehicle after a crash test. Therefore, you can see that there is no compromise. And for a full frontal or offset frontal test, the same applies. You can see the signals are again showing that the vehicle is not compromised in terms of safety, and you can see every and each crash testing scenario is being again simulated according to the standard, and we see that the lightweight version of the vehicle is still good enough in terms of safety. Then we can talk about how much is the decision. Here in this chart you can see at the end of the day for a full composite version you have a cost premium up here. But you remember at the beginning of the project or research, we actually decided on 10% of the retail price, which is like around here. So then this is the point that you are after. Which parts will be able to transform? Not all of them, but here this is the baseline, somewhere in between, and that's logical, right? But which parts? Then you have the information of what is the cost of each transformation over here. Then you can find out which parts will be transformed very easily. This is a very good decision-making tool for any composite transformation research. Okay, I don't know if I have time. I have a third part that is related to multi-scale design and modeling of composites and processes. There are a few examples that we have performed here, including again we can model concrete-like structures. You have seen short fibers, long fibers, or sandwich panels or laminates. With this methodology, we also can very easily model the length scales you have seen in the woven fabric composite version of the uncontained engine failure research, that we can model every and each fibril and fibers and wraps and fills, and you can see here the detailed model of weave structure very easily. You can see the length scale starts from here at the level of micrometers and all the way to the centimeters for the macro scale. And in between over here we call it in the literature as mesoscale. Therefore, in all scales, we can actually perform our analyses and model the structures accordingly, depending on our expectations and requirements. So, if a macro-mechanical model is enough, there is just no need to go to deeper and model your structure in the micro-mechanical level, because it is costly. It's naturally requires much more attention and computational power. Here you can see also some examples for the multi-scale modeling. Here the key is actually the homogenization here that we are talking about. Every scale change requires some level of homogenization, because there should be a bridging from a micro level to meso and meso to macro, and you have to then come up with a homogenization methodology, which is an active research topic. Here we have braiding, for example. Here you can see braiding for simple filament winding, or braiding for fibers that are like two parts or two components. and braiding for a three-dimensional weave structure. Here there is also another example for multi-scale modeling in terms of draping analysis or computations for draping. You can see here the level of anisotropy is quite high, and the methodology have successfully performed here. And you can see these are the material axes or in primary directions for the stress tensor and orientation. You can see in different orientations our computations have successfully performed the strong anisotropy. It's quite challenging. Another draping analysis you can see here for a 0-degree layer. You have an S-shape curve with a cross-section in the form of U-shape, and this is the results for these are the results for 0 degree. And when it is, by the way, it's 2 degrees on top, and when it is like 45 degree, you can see the differences. And when it is like 30 degree, it's all again changing. So this is also a draping analysis for strong anisotropy. There is also another example for organasheet. Organasheet is also thermoplastic, supported by a fiber. You can see it's hot form and consolidated in this section, in this form. And you can see the grid lines have been actually validated quite well with the simulation results in this case for an organasheet example. It's also possible to model methodologies or processes like RTM or infusion. It's basically quite easy. Here you can see injection of the resin under the condition of same porosity in all directions. You can see it's uniformly actually distributing, and if there is a porosity in X direction, so it's actually arrested in that direction and cannot move that easily. And the same applies for the Z direction over here for the injection of the resin. And in the form of a part in RTM or transfer molding, if the resin is actually injected over here, and if there is porosity over here, the analysis show the inclusion, if there is an inclusion over here, we can see that the results can be seen for an RTM type of process simulation. So my presentation ends. Thank you for listening and for your time. I can answer if there is any question.
Yeah, I heard something about the car engine body. They are trying to produce car engine body with composite materials, just to putting the cylinder housing,
yeah,
metal, the other side of the composite. Is that right? Have you heard about this kind of things?
I haven't heard, but I think it is possible if additive manufacturing is also involved. Like we can think of a composite by also additive technology is incorporated. Actually, we have some experiments over those technology, but it's in defense industry. The problem there is the low TG of polymers or plastics or composites. So if you back up with a ceramic backing or front, I think that's possible. That's what my interpretation of this. Yeah. But specifically, I haven't heard of it.
And another question, now is on the car industry about 13 or 14% plastic material. What do you think in the future? What will be this percentage?
Definitely, it's gonna increase. Definitely, especially since we have now out of autoclave technology and thermoplastics. It is now almost at the range of 1 minute per piece. That means that is, I think, gonna be very appropriate for automotive. The only thing is the foundation, investments for the foundation of this manufacturing technology, because it also requires some sophisticated cooling technologies for hot presses, for example, which is very, fast cooling equipment will be required. Other than that, I think in injection molding, it's already there. I have seen a couple of very good examples. I think the ratio will increase drastically. Yeah. Yeah. Thank you. All right. Thanks again for listening.
Aerodinamik olarak, yani bizim sürekli aslında ama central gravity bu reduction of weight sırasında değişmiş olması lazım. Bu durumda aerodinamik olarak da arabanın içlenmesi ve simüle edilmesi gerekir. Bunu yapan bir ekip var mı ayrıca? Oldu mu bir projede?
Tabii ya, bunlar
çünkü arabayı gelişigüzel hafifletemezsiniz.
Edemezseniz bu zaten tık onayına da alakalı.
Değil mi?
Onayını değiştirirler.
Motor gücüyle de ağırlık arasında bir ilişki var zaten.
Evet. Ama sıkıntısını gösterdim ya. Sıkıntısı zaten ağırlık dağılımı. Yani. Evet. Dolayısıyla onun değişmediğini gösterebiliyorsak zaten birbirimizi sağlamış oluyoruz.
Murat Bey, çok teşekkür ederim. Gerçekten çok faydalı oldu. Yani bugünün en iyi sunumlarından bir tanesi, benim de çok faydalandığım bir sunumdu. Ben PAGEV adına danışmanlar kurulu üyesi olarak size bu plaketi takdim etmekten gurur duyuyorum. Gerçekten.
Tamam.
Şöyle yapayım. Ha şunu kaldıralım. Tamam. Şöyle esnasında bir şey. Onu bırakalım. Karabük sıkıştıracağız.
Ben de